In 1896, Röntgen produced this radiograph, establishing X-ray imaging. This visual contrast is a map of absorption. Denser matter, like bone calcium or metal rings, blocks high-energy photons, while soft tissue lets them pass. This shows bulk density, but for locating individual atoms, absorption is useless. To map precise atomic coordinates within a crystal lattice, we rely on a different mechanism, diffraction. Light microscopes use diffraction to see small objects by bending visible light through lenses. But we cannot just build an X-ray microscope to look at atoms. Because atomic structures won't show up as shadows from absorption, we have to capture the photons they scatter and interpret those patterns instead. An optical microscope forces visible light to change speed as it enters a glass lens, bending the light to focus on a single sharp point. This electromagnetic spectrum chart shows hard X-rays far right of visible light. At these extreme frequencies, dielectric polarizability drops off completely. The polarizability of any lens material approaches the exact value of an empty vacuum. Consequently, the refractive index for X-rays is essentially 1. Without a difference in refractive index, like moving from air into glass, X-ray waves will not bend. This means manufacturing a physical refractive lens for X-rays is physically impossible. When an object scatters X-rays, those waves travel outward. Without a physical lens to bend them back together, we cannot directly project molecules onto screens. To circumvent this absolute limitation, crystallographers build computational lenses, using mathematical superposition to reassemble scattered waves. This diagram shows a propagating electromagnetic wave. Notice the electric field vector, E, and the propagation wave vector, S0. When an X-ray travels through matter, it interacts with electrons almost exclusively through that oscillating electric field vector. The incoming wave vector, S0, points in the direction of travel, and its magnitude is defined mathematically as exactly 1 over the wavelength, lambda. Many textbooks imply that coherent diffraction requires multiple parallel waves to arrive in perfect synchronized phase. That is incorrect. A single X-ray photon actually travels as a fully independent wave packet, possessing its own internal coherence length. When this single wave packet strikes an atom, its electric field simultaneously excites all the electrons that fall within that specific coherence length. In a process known as Thomson coherent elastic scattering, those excited electrons act as secondary sources, immediately emitting their own partial waves outward in multiple directions. Because this is an elastic process, no energy is transferred. The newly scattered wave vector, S1, maintains the exact same magnitude of 1 over lambda, preserving the critical phase relationships between the partial waves. These vector diagrams illustrate a scattering event. The black vector, S, represents the momentum transfer. We find the scattering vector S by calculating the precise geometric difference between the scattered wave S1 and the incoming wave S0. The length of vector S scales directly with the scattering angle, reaching its maximum possible magnitude during a 180-degree backscatter. Whether a photon actually lands on a detector at one of these specific angles depends entirely on how the partial waves, emanating from the electrons, interfere with each other along the way. This graph plots the traditional superposition of two continuous sine waves to calculate that interference. Using this graphical method, the amplitudes of the partial waves must be summed manually at discrete points across the entire 2π period to find the shape of the resulting wave. If the two waves are shifted by exactly pi, or 180 degrees, the amplitudes cancel each other out completely, resulting in maximum destructive interference. Tracing continuous curves is a perfectly fine method for adding two simple waves. But if you need to superimpose billions of waves scattering from a complex protein crystal, it creates a massive computational bottleneck. Bypassing that bottleneck requires abandoning trigonometry for a different mathematical architecture. Instead of treating the wave as a continuous undulating line, we split it into two static independent properties, amplitude and phase. This diagram represents the complex number plane, also known as an Argand diagram, which serves as the canvas for this calculation. We map the wave as a single vector. The horizontal real axis defines the real part of the wave, calculated as the amplitude multiplied by the cosine of the phase angle. The vertical imaginary axis defines the perpendicular component, calculated as the amplitude multiplied by the imaginary unit I times the sine of the phase angle. The bridge between the physical wave and the complex plane is Euler's formula, which states that e to the power of I times phi equals cosine phi plus I sine phi. This transforms a dynamic, oscillating physical sine wave into a static mathematical vector. This diagram shows vector addition in the complex plane, demonstrating how this translation solves the superposition problem. Calculating wave interference is no longer an exercise in plotting continuous curves. It becomes simple geometric head-to-tail addition of complex vectors. This exponential summation equation is our computational lens. It bypasses the need for physical optics, allowing us to mathematically reconstruct the combined diffracted wave. This mathematical abstraction connects directly back to the physical location of electrons inside a crystal lattice. Every electron occupies a physical position, vector r, dictating the exact phase angle of the scattered wave. We find this phase angle, phi, by multiplying the dot product of the scattering vector s and position r by 2 pi. This diagram shows why phase sign precision is critical. A negative structure factor, minus f, represents a 180-degree shift, causing destructive interference. This differs from the conjugate structure factor, f of minus phi, which vertically mirrors the phase angle across the real axis. If we know the exact physical 3D coordinate for every electron in the lattice, we can feed the r vectors into our mathematical lens and perfectly calculate the amplitude and phase of the resulting diffracted wave. Euler's formula and complex vector addition provide a flawless theoretical framework for reconstructing scattered waves, but applying that theory requires physical data, which brings us to the hard limitations of laboratory hardware. Modern X-ray detectors are simply photon counters. They tally the raw number of wave packets striking specific pixels on a sensor. Counting those impacts gives us exactly half of our complex vector, the overall magnitude or amplitude. But X-ray detectors cannot measure the exact time of arrival for individual photons. The moment a photon strikes the detector, its relative phase angle is permanently lost. We have built the perfect mathematical lens, but our hardware only captures half the required data. Extracting the missing phase angles from pure amplitude measurements is the defining obstacle of crystallography, known universally as the phase problem. We can fire high-energy X-rays through perfectly ordered biological crystals and capture the exact trajectories of the scattered photons. But the detectors we use to record this data are physically blind to half the quantum reality they observe. To understand what the detector is missing, we look to the structure factor equation. This equation defines the total structure factor by calculating the contribution of every atom. We account for its scattering power, the attenuation caused by thermal vibration, the B factor, and its fractional occupancy at that site. All parameters resolve into a single complex vector, but we are limited by a principle of quantum mechanics. The observable measurement of any complex wave function must be a real scalar value. Physical X-ray detectors cannot measure the actual phase of an incoming wave. They only count raw photon impacts at a spatial coordinate over time, resulting in a flat intensity value. Because of this, the detected intensity equals the square of the structure factor amplitude. Squaring the amplitude erases the phase angle from the data. Without those phase angles, working backward from a diffraction pattern to reconstruct the 3D electron density of a molecule is mathematically impossible. This loss of data is the crystallographic phase problem. Because the phase data is missing, the map of reciprocal space appears as a perfectly mirrored symmetrical geometry. This symmetry is codified as Friedel's law. It states that in standard X-ray scattering, reflections on opposite sides of the origin will always display identical intensities. We map a standard Friedel pair on the complex plane. Reflection HKL and its inverse share equal amplitudes and conjugate phase angles, but detectors only see amplitude. With phases hidden, these identical intensities are the only measurements we collect. To solve for the missing phases, we need distinct variables. Because Friedel pairs yield perfectly equal amplitudes, we have no comparative leverage to calculate the difference. Building a more sensitive detector does not fix a symmetry inherent to the diffraction geometry. To extract the phases, we must find a way to introduce a directional bias into the lattice calculations from the inside out. This is why crystallographers use tunable synchrotrons. We can precisely dial the incident X-ray energy to match the resonance frequency of a specific heavy atom within the crystal. In standard scattering, X-rays bounce off the outer valence electrons, but at resonant energies, the photons interact directly with the tightly bound core electrons. The spectroscopic term scheme shows these atomic energy shells. The energy required to disrupt them increases closer to the nucleus. By tuning the beam to eject an electron from the 2p3/2 core level, we create an L3 absorption edge. The L3 edge is a powerful target because the 2p3/2 level holds 4 degenerate electrons, twice as many as lower levels. This significantly increases the probability of an X-ray being absorbed. This absorption coefficient graph shows the result. When the beam hits that core electron requirement, we see a massive, stepwise spike in how the atom interacts with the X-rays. At this exact energy, the heavy atom ceases to be a passive scatterer. It becomes a dampened quantum oscillator. If we examine that absorption spike at high resolution, we find that the clean theoretical step is actually preceded by a jagged fine structure. This near-edge structure contains a sharp feature called the white line peak. This peak occurs because photoelectrons transition into unoccupied orbital levels immediately before they are ejected from the atom. It represents the point of maximum resonance. Because of this behavior, the standard atomic scattering factor used in our original equation is no longer sufficient. We must expand the equation to include 2 wavelength-dependent terms, a real dispersive term, F', and an imaginary absorptive term, IF'. Through the Kramer's chronic transform, as the absorption factor spikes, the dispersive term plunges into a deep negative trough. By tuning the synchrotron beam to this edge, we introduce a non-zero imaginary component into the scattering factor. This addition disrupts the perfectly mirrored math of the unit cell. We can visualize this disruption on the complex plane. We start again with our standard symmetrical Friedel pair. When we apply the dispersive term, F', it equally shrinks the overall length of both vectors. The mirrored symmetry remains. Next, we apply the imaginary term, F'. Because multiplying by I forces a 90-degree phase shift, both new vectors point in the same vertical direction on the complex plane. Because both imaginary vectors point up, they add to the length of the top Friedel mate, but they cut across the geometry of the bottom mate. The centrosymmetry of the system is broken. This specific Friedel pair now produces different intensity values on the detector, creating a measurable gap where there was previously a perfect mirror. This gap is the anomalous Bivote difference, an intensity change caused purely by the resonance of the heavy atom. By measuring this difference, we extract the variables needed to isolate the positions of the heavy atoms from the rest of the protein. A single measurement is just the start. To calculate a complete phase map, we need a system of distinct comparative data points. This is the multi-wavelength anomalous diffraction strategy, or MAD. We harvest data at 3 highly specific energy targets along the absorption edge. At the peak, shooting exactly at the white line maximizes the F'' term, giving us the largest possible anomalous differences within the dataset. At the inflection point, we maximize the negative dip of the F' term. This creates significant dispersive differences when we compare this entire dataset against the others. Finally, the remote point provides a stable baseline, where the resonance effects are minimized, acting as our control. By cross-referencing the dispersive differences between datasets with the anomalous differences within them, we create a solvable system of equations. Solving this matrix provides the phases of the heavy atoms, which act as the anchor to mathematically determine the missing phases of the entire protein. The intensity measurement of a single reflection no longer hides the phase. By utilizing the resonance effects at the absorption edge, we recover the directional data needed to calculate the electron density map and reveal the protein's atomic structure.